A load factor is the ratio of the average load to the maximum load. For residential applications, a load factor of 0.6 to 0.7 is typically considered. For commercial applications, the load factor ranges from 0.75 to 0.85. In industrial settings, a load factor of 0.8 to 0.9 is common. Spare capacity is the difference between the transformer's rated capacity and the maximum expected load. For residential projects, a spare capacity of 25 to 30% is generally recommended. Commercial projects typically require a spare capacity of 15 to 20%. Industrial applications usually need a spare capacity of 5 to 10%. Different types of transformers are suited for various applications. Dry-type transformers are often used in areas where fire resistance is critical, such as offices and hospitals. Liquid-filled transformers are commonly used in industrial applications and substations. Pad-mounted transformers are frequently used outdoors in residential and commercial areas. The National Electrical Code, or NEC, mandates several protection requirements for transformers. All transformers must be protected against excessive current. Primary protection is achieved through a fuse or circuit breaker installed on the primary side of the transformer. Secondary protection is provided by a fuse or a circuit breaker on the secondary side. Transformers must be grounded to protect against electrical faults. Primary grounding involves connecting to the grounding electrode system through a grounding rod or plate. Secondary grounding involves connecting a grounding wire to the transformer's frame or enclosure. Transformers should be protected against voltage surges, which can damage the windings. Surge protectors can be installed on the primary or secondary side of the transformer. Additional protection measures include temperature sensors, pressure relief valves, and bushing inserts. Temperature sensors monitor the transformer's temperature to prevent overheating. Pressure relief valves release excess pressure in liquid-filled transformers to prevent explosions. Bushing inserts prevent moisture and contaminants from entering the transformer through the bushings. When sizing a transformer, several factors must be considered to ensure it meets the demands of the electrical system while adhering to safety standards outlined in the NEC. The NEC provides guidelines for load calculations, overcurrent protection, and grounding, which are critical for safe and efficient transformer operation. The load factor is a crucial parameter in transformer sizing. It represents the ratio of the average load to the maximum load over a period, typically a day or a month. A higher load factor indicates a more consistent load, whereas a lower load factor suggests intermittent or peaky demand. In residential applications, the load factor typically ranges from 0.6 to 0.7, reflecting the varied usage patterns of household appliances and lighting. Commercial buildings, with more consistent operation hours and equipment usage, usually have a load factor between 0.75 and 0.85. Industrial facilities, often running heavy machinery and equipment continuously, can exhibit load factors from 0.8 to 0.9. Understanding the load factor helps in accurately estimating the transformer's required capacity, preventing both undersizing, which can lead to overheating and failure, and oversizing, which results in unnecessary costs and reduced efficiency. Spare capacity is another critical consideration. It refers to the additional capacity built into the transformer beyond the expected maximum load. This buffer is essential to accommodate future load growth, unexpected surges, or temporary overloads without stressing the transformer. For residential installations, a spare capacity of 25 to 30% is commonly recommended. This allows for the addition of new appliances or electrical devices without exceeding the transformer's rated capacity. Commercial projects typically require a spare capacity of 15 to 20%, accounting for potential expansions or changes in business operations. Industrial applications, which often involve significant capital investments and long-term planning, may only need a spare capacity of 5 to 10%, assuming that load requirements are well-defined and relatively stable. The type of transformer selected should match the application's specific requirements and environmental conditions. Dry-type transformers are frequently used indoors due to their fire-resistant properties and minimal environmental impact. They rely on air circulation for cooling, making them suitable for locations where liquid-filled transformers pose a risk of leaks or spills. These transformers are commonly found in office buildings, hospitals, schools, and other public facilities. Liquid-filled transformers, typically using oil or synthetic coolant, offer superior cooling capacity and are ideal for high-power applications. They are often used in industrial plants, substations, and large commercial complexes where substantial electrical loads need to be supported. Pad-mounted transformers are designed for outdoor use and are commonly installed in residential and commercial areas. They are enclosed in a tamper-resistant cabinet and placed on a concrete pad, providing a safe and aesthetically pleasing solution for distributing power in densely populated areas. The NEC mandates comprehensive protection measures to ensure transformer safety and prevent electrical hazards. Overcurrent protection is a fundamental requirement designed to protect the transformer from damage caused by excessive current flow due to overloads or short circuits. Primary overcurrent protection is typically provided by fuses or circuit breakers installed on the primary side of the transformer. These devices are selected based on the transformer's rated current and inrush current characteristics. The NEC specifies maximum overcurrent protection ratings to prevent nuisance tripping while still providing adequate protection. Secondary overcurrent protection is similarly provided by fuses or circuit breakers on the secondary side. These devices protect the downstream circuits and equipment from faults originating within the transformer or the connected loads. Ground fault protection is another essential safety measure. It detects and interrupts ground faults, which occur when current flows through an unintended path to ground. Ground faults can pose a significant shock hazard and cause extensive damage to electrical equipment. The NEC requires transformers to be grounded to provide a low impedance path for fault current, facilitating the operation of overcurrent protection devices. Primary grounding involves connecting the transformer's primary winding neutral to the grounding electrode system, which typically consists of grounding rods, plates, or building steel. Secondary grounding involves bonding the transformer's secondary winding neutral to the grounding electrode system, ensuring that all exposed metal parts are at ground potential. Surge protection is necessary to protect transformers from voltage surges caused by lightning strikes, switching operations, or other transient events. Voltage surges can induce high stresses on the transformer's insulation, leading to premature failure. Surge protective devices, or SPDs, are installed on the primary and secondary sides of the transformer to divert surge current to ground, protecting the transformer windings from damage. These devices are selected based on the expected surge voltage levels and the transformer's insulation withstand capability. In addition to these primary protection measures, other protective devices and monitoring systems can be implemented to enhance transformer reliability and safety. Temperature sensors monitor the transformer's internal temperature, providing an early warning of potential overheating conditions. These sensors can trigger alarms or automatically shut down the transformer to prevent damage. Pressure relief valves are used in liquid-filled transformers to release excess pressure caused by internal faults or overheating. These valves prevent catastrophic failures and reduce the risk of explosions. Bushing inserts are used to seal the transformer bushings, preventing moisture and contaminants from entering the transformer and compromising its insulation. Regular inspection and maintenance are essential to ensure the continued safe and reliable operation of transformers. This includes visual inspections, insulation testing, oil analysis, and periodic replacement of worn or damaged components. Adhering to the NEC guidelines and implementing these protection measures will help to ensure the longevity and safety of transformer installations. Understanding these requirements is crucial for electrical engineers, contractors, and facility managers involved in the design, installation, and maintenance of electrical systems. The load factor plays a vital role in determining the appropriate size of a transformer for residential, commercial, and industrial applications. It's essentially a measure of how efficiently the electrical load is being utilized over a period. By understanding the load factor, electrical engineers can more accurately estimate the actual demand on the transformer and avoid oversizing, which can lead to inefficiency and increased costs. Residential load factors generally range from 0.6 to 0.7. This reflects the intermittent and variable nature of residential electricity consumption. During the day, when most residents are at work or school, the load is relatively low. However, in the evenings and on weekends, the load increases significantly as people use appliances, lighting, and electronic devices. A lower load factor indicates that the peak demand is much higher than the average demand, requiring the transformer to be sized accordingly to handle these surges in power consumption. Commercial load factors typically fall between 0.75 and 0.85. Commercial buildings often have more consistent electricity usage patterns than residential properties. Businesses tend to operate during fixed hours, and equipment like computers, HVAC systems, and lighting are used throughout the day. However, there can still be variations in load depending on the type of business. For example, a restaurant may have a higher peak demand during lunch and dinner hours, while an office building may see a surge in power consumption in the morning when employees arrive and turn on their computers. Industrial load factors tend to be the highest, ranging from 0.8 to 0.9. Industrial facilities often operate heavy machinery and equipment continuously, resulting in a more stable and predictable electrical load. However, even in industrial settings, there can be fluctuations in demand depending on production schedules and equipment maintenance. A high load factor indicates that the transformer is being utilized more efficiently, which can lead to lower energy costs and improved overall system performance. Spare capacity is the additional capacity built into the transformer beyond the calculated load requirements. It is essential for accommodating future load growth, unexpected surges in demand, and temporary overloads. Providing adequate spare capacity ensures that the transformer can operate safely and reliably without being stressed beyond its design limits. For residential applications, a spare capacity of 25 to 30% is generally recommended. This allows for the addition of new appliances, electronic devices, or even a small home office without overloading the transformer. As families grow and lifestyles change, electricity consumption tends to increase, making it crucial to have sufficient spare capacity to handle these future demands. Commercial projects typically require a spare capacity of 15 to 20%. Commercial buildings often undergo renovations or expansions, and businesses may add new equipment or technology over time. Having spare capacity allows for these changes without requiring a complete transformer replacement. In some cases, businesses may also choose to install additional equipment to increase productivity or improve efficiency, which can lead to higher electricity consumption. Industrial applications usually need a spare capacity of 5 to 10%. Industrial facilities typically have well-defined load requirements, and future growth is often planned in advance. However, even in these settings, it is essential to have some spare capacity to handle unexpected surges in demand or to accommodate new equipment that may be added in the future. The type of transformer to be considered depends on the specific application and the environment in which it will be installed. Dry-type transformers are commonly used in indoor applications where fire resistance is critical. These transformers rely on natural air convection for cooling and do not use any flammable liquids. They are often found in office buildings, hospitals, schools, and other public facilities where safety is a top priority. Liquid-filled transformers, typically filled with oil or a synthetic coolant, are used in high-power applications where efficient cooling is essential. These transformers are commonly installed in substations, industrial facilities, and large commercial complexes. The liquid coolant helps to dissipate heat more effectively than air, allowing the transformer to operate at higher loads. Pad-mounted transformers are designed for outdoor use and are typically installed on a concrete pad. These transformers are commonly found in residential and commercial areas where underground power distribution is used. They are enclosed in a tamper-resistant cabinet to protect them from vandalism and the elements. According to the NEC, overcurrent protection is a fundamental requirement for all transformers. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect the transformer from damage caused by excessive current flow due to overloads or short circuits. The NEC specifies the maximum allowable overcurrent protection ratings for transformers based on their kV/ampere rating and primary and secondary voltages. Primary overcurrent protection is typically provided by a fuse or circuit breaker installed on the primary side of the transformer. This device protects the transformer from faults originating within the transformer itself or in the primary distribution system. The NEC specifies that the primary overcurrent protection device should be sized no greater than 125% of the transformer's rated primary current. Secondary overcurrent protection is provided by a fuse or circuit breaker installed on the secondary side of the transformer. This device protects the secondary distribution system and connected loads from faults originating within the transformer or in the secondary wiring. The NEC specifies that the secondary overcurrent protection device should be sized no greater than 125% of the transformer's rated secondary current. Ground fault protection is another essential safety measure required by the NEC. Ground faults occur when current flows through an unintended path to ground, such as when a live wire comes into contact with a grounded metal object. Ground faults can pose a significant shock hazard and can also cause fires. The NEC requires transformers to be grounded to provide a low impedance path for fault current, allowing the overcurrent protection devices to quickly clear the fault. Grounding is typically achieved by connecting the transformer's neutral point to a grounding electrode system, such as a ground rod or a metal water pipe. Surge protection is necessary to protect transformers from voltage surges caused by lightning strikes, switching operations, and other transient events. Voltage surges can damage the transformer's insulation and windings, leading to premature failure. The NEC recommends the use of surge protective devices, or SPDs, to protect transformers from voltage surges. SPD are typically installed on the primary and secondary sides of the transformer to divert surge current to ground, protecting the transformer from damage. The selection of SPD should be based on the expected surge voltage levels and the transformer's insulation withstand capability. In addition to these primary protection measures, other protective devices and monitoring systems can be implemented to enhance transformer reliability and safety. Temperature sensors can be installed to monitor the transformer's winding temperature and provide an early warning of potential overheating conditions. Pressure relief valves can be installed on liquid-filled transformers to relieve excess pressure caused by internal faults or overheating. These valves help to prevent catastrophic failures and explosions. Regular inspection and maintenance are essential to ensure the continued safe and reliable operation of transformers. This includes visual inspections, insulation testing, oil analysis, and periodic replacement of worn or damaged components. Adhering to the NEC guidelines and implementing these protection measures will help to ensure the longevity and safety of transformer installations in residential, commercial, and industrial projects.